Hi, this is question number 4 from the paper May 25, paper 2, time zone 1. Okay, so let us read the question statement. They say a system consists of 10 distinguishable particles which can swap their energies, which can exchange their energies in the integer multiple of a constant value E. Okay, but if you add up all the energies of the system, then that is a 10E. Okay, so in this question, basically we have to find out that which one of these two configurations have a more number of microstates. So dear students, this is a question about the uh, B.4 thermodynamics, right? In which we will see that logically that which have more number of microstates. But let us quickly understand what is exactly the microstate. And for this, I will explain you in a context of this definition. Okay, so microstate is actually are the all the possible ways in which you can distribute the energy among these particles. For example, in this diagram you see that all of these particles have uniform energy, same energy, right? But all of these particles, they have a different energies. Okay, so this is a one configuration and this is another configuration. So we will see that how many more possible ways we can drive out of these configuration in which we can give the energy to the particle. But remember one thing, the total energy sum should be 10E. Okay, so let me write first the definition in this context. Possible ways in which energy can be distributed. Okay, students, now I explained you more about it. That let's say these are the two containers. Okay, these are the two containers, and once again, in which there are the same 10 particles. Okay, the one container shows the configuration A. Okay, and actually, I'm explaining you that which have a more number of microstates. For this thing, I am drawing these diagrams. Okay, so you see that these are the 10 particles: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now remember, all of them have same energy according to configuration A. But what about the configuration B, right? The one have energy 4E. So let's say it have energy 4E, the one has energy 3E, another have energy 2E, and then this is E, and these are the particles which have a no energy. So they are in the zero energy level here. Okay, so there are total 6 particles. Okay, now I explain you, rather than explaining you from the mathematical equation, I just tell you conceptually, right? One of these configuration have more number of microstates, which one in which the particles can swap their energies. Okay, swap their energies. Okay, so for example, if this particle is going to hit this particle, right, according to kinetic molecular theory, we know that their collision will result an equal transfer of energy, will the transfer of whole energy, right? So when this will particle will hit with this particle, they will transfer their energy but remain the, even after collision their energy will remain E. Okay, so you can see that what with whatever the particle, the two particles collide in this combination, dear students, in this combination you will always have after collision the same energy, right? So it means that there is a no other combination we can make. Okay, it is the most rare combination that all the particles have same energy, and this is only one way that they are transferring their energy. So this is the least possible. Okay, and right now it have a least entropy. And but if you see in the next diagram, if this particle is going to hit with this particle, right, they can swap their energies. Then they will have a different energy after collision. What about when it will hit with this particle? Then after collision its energy will become 4E and its energy will become 0. Okay, what about 2E when it will hit with this particle, right? After collision, its energy will be 2e and its energy will be 0 due to the elastic collision. So you see that we are having a huge amount of combinations that we can make, right? That's why it have more number of microstates, obviously, right? More number of microstates. So when it have a more number of microstates, obviously it should have the larger entropy. But I will explain you with another diagram, dear students. So this proves that it have a more number of microstates. Okay, before I move to the next method, okay, notice that the macrostate is same, right? What is a macrostate? Right now the macrostate is the total energy, right, which is 10e. Okay, no matter the particles will swap their energies, but the total sum of energy is 10e. That's why macrostate is same, but they configuration B can have a large amount of more microstates, okay, more combinations in which the particles have a different energies. Okay, now the method number two. Okay, so in this second method, as you see that the particles are already sharing the same energy, right? So even if they collide, the swap, they will have the same energy after collision. So there is actually the only one possible way that already exists that they have a same energy. So that's why it has only one microstate. Okay, I mean to say, even if the one particle hits with another particle, it can never jump, it can never go to the 2e, it can never go to the 3e, you understand? So that's why it have just one microstate. Okay, so they cannot move out of this energy level. Okay, so what about this? We may have a many combinations in a configuration B. The one combination that we already have, let me write it here. So I can write it like this, that this is a 4e, 3e, 2e, e, and then 0, 0, 0, 0, 0, and 0, right? This is already one combination. This one microstate is already given over here, right? What are the other combination, dear students? What about if I say that there are three particles, there are two particles in 3e. So the total energy is 6e, 6e, 4e is left. Let's say the one particle is here. 8e, one particle is here. 9e, okay. Now how many are left? So there's another particle over here, right? So five particles, I have adjusted them already. So the rest of the five are here. One, two, three, four, five. There's another combination. It has already exceeded than one microstate. So obviously it have more microstates. Okay. So I'm writing its combination 3e, 3e. So 2e, and then e, and then 0, 0, 0, 0, and 0, right? In the same way, you can, for example, write another combination. I am just showing you, so next time you can do it by yourself as well. So what about if I say there are three particles which have a same energy, 2e? So total is 3e. Okay, the one particle is here, 9e, one particle is here, 10e. It means that now we have how many? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So there are total 10 particles. I have adjusted. This is another combination. So now you understand that combination B have more number of microstates. So students, now let's move to the next question. But first see what the mark scheme says, that it have more number of microstates because there are more ways to swap the energy, exchange the energy. Okay. Now, what is our next question? In the next question, what will happen? How this configuration A will evolve or configuration B will evolve with the passage of time? What will happen? The process one says that the system is initially in a configuration A, but eventually it will evolve to the configuration B. Okay, and the system is initially in a configuration B, then it will evolve to the A. So let us see which one is correct. Okay. Now here I would like to mention the second law of thermodynamics, right? Because second law of thermodynamics say that if your system is not reversible, then the net change in entropy will be always positive. Okay, right? So I can say there is a net change in entropy is always greater than zero. For a reversible process, it is zero. Okay, but for this process, it will be more than zero. It means that The change in entropy is always positive. It means that any natural process, it always proceed from the less entropy to the more entropy, from more organized to the less organized. You understand? You know that always the heat goes from the hot reservoir to the cold reservoir. A hot cup of coffee will become cold, or it will get an equilibrium temperature after some time. Why? Because its heat will transfer to the environment. So your environment is a sink, your environment is a cold reservoir. Okay, so all the natural systems move from the less entropy to the higher entropy. Okay, it means that that's why the change in entropy is always positive. Now, when we see our microstate, and by the way, you know this equation already, that S is equals to Boltzmann constant natural log of number of microstates. So your entropy is directly proportional to the natural log of the number of microstates. It means that if your configuration, which configuration have a more number of microstates, obviously configuration B, so it have a higher entropy without a doubt. You understand? And this have a less entropy. It means that our system will evolve from, dear students, from A to B, from a less entropy to the higher entropy, okay, towards the more disorganized system. Okay, so that is the reason. So we have already discussed these points, for which you will be rewarded 3 marks. Second law of thermodynamics, we have discussed it. Okay, and the entropy is always greater in a configuration B because it have a more number of microstates, and so the it will evolve to the configuration B. So the process 1 is correct. I hope you understand this solution.